Hey everyone, welcome back, and today let's solve Leetcode problem 42 titled Trapping Rainwater. So we're given n non-negative integers representing an elevation map where the width of each bar is 1 and we need to compute how much water it can trap after raining. So in example 1 they also give us an image to better visualize this. So as you can see, our heights is simply going to be an input array of different heights for different bars, and our output would be 6. Why is our output 6? Of course, that's how much water we can actually trap, or rather rainwater. But why is that? See, it says that the above elevation map, the black section, is represented by an array of 0, 1, 0, 2, 1, 0, 1, 3, 2, 1, 2, 1. And in this case, 6 units of rainwater, the blue section that it covers, is going to be trapped, right? For this part, or window I should say, for this kind of window, we have this much water in the blue section being trapped. For this window, we have this much water, and for this window, we have this much water. And if you count that up manually, you'd see that be 3 plus 1 plus 1 plus 1, or 3 plus 3, which is 6 units of water being trapped as a whole. In example 2, we have the input array height to be the following, and we output 9, because again, that would be the amount of water we can actually trap, or the blue section we can actually form with the different bar heights that they give us in our input array height. So with that out of the way, I will give you guys a few seconds. I'm going to just go over this problem in your head and think of a valid solution. And then I'll show you guys how I would optimally solve this problem in a few seconds. Okay, so to solve this problem efficiently, we're going to be using our standard two-pointer approach, because of course that lets us avoid our nested loops or our brute force solution, which actually reduces our time complexity from big O of n squared to big O of n, right? A linear time solution. So kind of the high level kind of breakdown of the algorithm, we're going to use 2 pointers. I'm going to say left and right, initially pointing to the start and the end of our input array heights. And we're also going to track the maximum heights on the left and the right sides as, left max and right max. And as we move the pointers inward, we have to calculate and accumulate the trapped water based on the minimum of left max and right max heights. Okay, so again, left is going to be a pointer that starts at the beginning of the array. Right is going to be a pointer that starts at the end of the array. And our left max is going to be the maximum height encountered from left up until the left pointer. And our right max is going to be the maximum height encountered from right up until that right pointer. And we're going to have another variable, water trapped, which is going to store the total amount of water trapped, which is going to be initialized to 0, and also the value that we're going to return. Okay, so a pretty quick base case here that I like to have for problems especially like this. If not height, so if our height input array is actually null, it doesn't have any nodes or bar heights, then we can immediately return 0. Why? Because we don't actually have any bars, we can't trap any water without bars, and so we can immediately return 0 units of water being trapped, right? We have nothing, or we don't have any resource to actually trap any water, regardless of how much water actually falls. Now we can actually initialize our 2 pointers, left and right, and like we talked about before, it's going to be initialized to 0 and the last index, or the length of the height minus 1 of our input array height. Okay, well again, left is going to be initialized to the beginning of the array, right is going to be initialized to the end of the array, and these pointers are going to help us traverse the array from both ends towards the center of our input array height, right, to actually check all the different bars that we could potentially use for different bar heights for the current window that we're trapping rainwater for. Okay, so once we do that, now we can initialize our left max and we can initialize our right max variables, and like we talked about before, these are going to be initialized to the height at the left index, which again is initialized to 0. I realized that I spelled this completely wrong. Height. Okay, that should be right. And we're going to initialize right max to be height, you guessed it, index right, which again is initialized to the last index of our input array height, right? And what are these variables going to do? They're simply going to keep track of the maximum heights that we encounter on each side, left and right, as we actually move the pointers inward of our input array heights. Okay, so now we can actually finally have our last variable that we need, water trapped, which is the variable that we're going to return, initialized to 0, which is going to store the total amount of water trapped as we actually calculate it, as we accumulate it through different windows or bar heights that accumulate or trap rainwater. So now, while our left pointer or index is less than the right pointer, so all we actually have a loop that marks that kind of checks that our left pointer is in bounds of the right pointer to ensure that we haven't actually traversed the entire array with our 2 pointers without actually covering any duplicate values from duplicate indices, right? While that's actually true, now we have to check if the left max is less than the right max. What is this saying? It means if left max is less than right max, if that's true, that means we should process the left side of the array, because again, the amount of water trapped on the left is determined by that left max variable. So if that's true, if that's the case, then we can initialize, or rather update our left by 1, right? Again, note that left is going to be our index that we move 1 to the right, right? We're just moving right to our input right nums, right? Because we're simply processing the left side, and so we have to just move our pointer 1 step to the right. Now, once we've done that, now we can initialize our left max to be the maximum of course itself, because we don't want to make it smaller. Oops. Maximum of course itself. Again, we don't want to make it smaller, that variable. And heights at left, the new index that we've kind of encountered as we incremented our left index by 1, as we moved to the right of our input array height, again, while we're in bounds of right. So while left is still less, or rather, while left is still less than right. Okay, great. And then, once we do that, now we can actually water trapped plus equals increment the number of water, or rather the units of water that we've actually had, left max, minus the height at index left. Okay, yeah, completely butchered that. Left max minus height at the index left. Why do we do this? Because we have to actually subtract the height at left because from left max. Why? Because that's going to represent the water that can be trapped at that position, and we have to add it to the water trapped variable, which is again going to be the kind of variable that we return, because that's going to represent the number of water, rather the number of units of water that we can return that's trapped within different windows of bar heights. Okay, that's determined by left max minus height at the index left that we're currently incrementing it to. But we'll have an else conditional. What is this else conditional checks? It checks when left max is not strictly less than right max. So if that's not the case, we have to process the right side instead. Why? Because the trapped water on the right is going to depend on that right max variable. So if that's the case, we can decrement right. We can decrement right by 1, right minus equals 1, because we want to now move to the left part of the array, to the center, right, while right is still greater than left, because we're now processing that right side. And we can now set right max, right, the maximum for the right side, to be equal to the maximum of course itself, because we don't want to make it smaller. And right max, rather, I'll say height at right. Height at index right. So pretty similar structure to this. We're simply just replacing right with, or rather left with right, because again, we want max height to be the maximum of its current value and the height at the new right position. Why? Because that's going to ensure that that variable right max is going to hold the highest bar height from the end up until that right pointer that we're traversing to the left of it, that we're decrementing. Okay, and then we can actually increment or update the number of water that we've stored, rather the units of the number of water we stored, so water trapped, I should say, plus equals incrementing it by the right max, again, this formula that we kind of derived, minus height at the right index, right? We simply have to subtract the height at that right index from the right max and add that value to the water trapped. And like we said before, that's going to kind of represent the water that can be trapped at that position, and we have to add it again to our water trapped variable. And ultimately, while this is true, while left is less than right, and we've processed all the different nodes or bar heights and our input array height, we can simply return water trapped. Again, like we talked about before, why? Because it's going to store the total number of trapped water, which is going to be our final result once our loop finishes, while left is no longer in bounds or less than right. So unless I made any syntax errors here, this should be accepted. And as you can see, this is just about as efficient as you can get. So to kind of reiterate, what does this code do overall? It's simply a standard two-pointer technique. We simply have to calculate the total water trapped between the different bars and their heights after it actually rains. Give me a minute. Let me just drink some water, guys. Right? How do we do this? We simply keep track of the maximum bar heights on both ends of our 2 pointers, left max and right max, and use those 2 pointers, left and right, to actually move inward toward the center while they're still in bounds of each other of our input array height. Right? And as we actually move or traverse through the center, we actually have to compare left max and right max to decide which pointer to actually advance, right, with these different conditionals. And for each position, we simply have to compute the trapped water by taking the difference between the maximum height and the current height and add that difference to our water trapped, or rather increment the difference to our water trapped variable to again store how many units of water that we trap between all the different bars and their corresponding heights. So for the time complexity, this is going to be big O of n because it's a two-pointer technique. We really only process every single node or bar in our input array heights only once. It's a one-pass solution, and so this is going to be a big O of n solution for runtime complexity. And our space complexity is going to be constant time, or big O of 1, because we're not actually using any extra data structures. We're simply using some extra integer variables like left max, right max, and the water trapped. It's going to be a constant time memory solution. So if you guys enjoyed this solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye bye.